Good morning. I hope everyone had a fun and relaxing spring break. I know I did. Welcome back, and I'm glad everyone's back here. This is going to be a lesson in our new unit on sequences and series. Okay, we had before the break a kind of an introductory lesson about what sequences were, and hopefully you're able to finish that before you went off on spring break. If not, I'll be around. All right, later on, as I mentioned in my announcement, we're going to be having a video conference later on this morning. Okay, or just send me an email and I'll answer your question. Okay, individually. Okay, so we want to expand our notion into from sequences into something called a series. Okay, now first off, remember that a sequence was a list of numbers that follow a pattern, right? So for instance, 1, 3, 5, 7, 9, ... that was a sequence that followed a pattern. Sequences could be infinite like this one, which the ... says it just keeps going, or it could be finite, 2, 4, 6, 8, where there's a certain specific finite number of values in the sequence. There's 4 of them there in this case. Yeah? All right. So that's a sequence. Okay. In general, we wrote a sequence that looked like this. A sub n was a sub 1, 2, 3, 4, and it just keeps going. Where this lists the terms of the sequence, and each term is seen as having a position in the sequence. That's the first term, that's the second term, that's the third term, that's the fourth term, and so on. So, theoretically, if we kept going, we'd have a 100th term, which we'd write as a sub 100, and so on, right? Okay, now, so for example, we could say a sub 100 is equal to 55. What that means is, for a given sequence, the 100th term in the sequence happens to be the value 55, right? Now, we also saw that typically when we worked and we designated sequences, they would have a formula that would generate any given term in the sequence. So something like this, for example, a sub n was equal to 4 plus n, where n, remember, is the term position, first term, second term, third term, fourth term, like this. And this would designate any value in the sequence. So for example, the first term, a sub 1, we said that was 4 plus 1, right, which is 5. So this would be a sequence with 5 as the first term. A sub 2 would be 4 plus 2, which would be 6, and so on, right? This allowed us to generate any term, any value in a sequence that we want. We just have to know which sequence we want. So for example, a sub 100 would be 4 plus 100, which is 104. So in this sequence, if we were to list them all out, starting with 5, 6, 7, 8, 9, 10, the 100th term would be the value 104. Yeah? Okay, so that's that. We also had a recursive formula, which we're not at this point going to use so much, but you should know from our first lesson what the recursive formula is. Okay? But we're going to move on a little bit. Okay, because we can generate terms in a sequence using these counting numbers, 1, 2, 3, 4, 5, 6, 7, to generate the terms in a sequence. Sequences are actually a kind of function, where the domain, okay, sequences are actually a kind of function, where the domain is equal to n, which is 1, 2, 3, 4, 5, etc., which if we want to can just keep going, right? So sequences, I'll write it right here, are a function, okay, and where the range is actually the terms of the sequence. So for example, this guy right here, 4n plus 1, the terms of the sequence, so 4n plus 4 plus n, right? That was 5, 6, 7, 8, 9, ... And so this would represent a kind of function where that was the 4n plus 1 is the equation of the function. Typically, when we think about sequences, when we work with them, though, we just the domain, the position numbers, the n numbers, 1, 2, 3, 4, 5, and so on, those are kind of assumed in the context of the problem, and we just work with the sequence values, which are in effect the y values of the function. Okay? All right, now, we're going to be working with these a lot, and they have a lot of uses, okay? From this, what comes from the idea of a sequence, the next thing along is the idea of a series. And this is going to be just like a sequence is a very important concept, a series is a very important concept, okay? And a series is simply this. If we start with a sequence, and write them as a sum, that's a series. Okay, so for instance, let's say this sequence we add up here, 1, 3, 5, 7, 9. The corresponding series would be 1 plus 3 plus 5 plus 7 plus 9, and then ... That could keep going. That would be an infinite series. Okay? Or let's say I could write 1 plus 3 plus 5 plus 7. That's a finite series where it's just the first 4 terms. Okay? Now you're thinking, okay, but so what? It's hard to see what's going on with this or why this concept is important right now, especially the concept of an infinite series. It turns out that they have some very surprising and useful properties, but more about that later on. Right now, I just want to focus on the definition and some certain kinds of introductory problems that we might have to do in working with a series. But keep in mind, what we mean by a series is a sequence where all the terms of the sequence are written out as a sum, just like that is. That's a series right there. Okay? So we could write a series that looks like this. Let's put that aside there. So here is another series. So we're still working a series here. So what if we had a sequence that looked like this? 1, 4, 9, 16, 25. Now that is a finite sequence. Okay? It's just a list of numbers that I hope you can see are just the square numbers, the first 5 square numbers, right? The corresponding series would be 1 plus 4 plus 9 plus 16 plus 25. That's the series right there. Now, since we're adding them, you can imagine that we could actually add those together if we wanted to, although we won't necessarily. So if we can add those together, 1 plus 4 plus 9 plus 16 plus 25, that works out to be 55. If we actually add them together, this is called the sum of the series. And a partial sum like this, it's called a partial sum because it's, we've only got a finite number of terms in a series, right? We'll always have a sum. And sometimes, a lot of times, we'll just go ahead and add them up, and that's called the sum of the series. And if your problem says evaluate the series, that's what they mean. You take the sums of that, you take the series and you actually add them together to get a single number, which is the sum. But when we talk about a series, we don't mean the sum. When we talk about the series, we mean the list of the numbers, the sequence where the terms have been added together, written out fair and square like that. That's the series. Okay? All right, very good. So that's the idea of a series. Now, series can be written also using a formula. For example, just like this sequence up here had a formula where a sub n was equal to n squared. The first term, 1 squared is 1. The second term, 2 squared is 4. The third term, 3 squared is 9. The fourth term, 4 squared is 16. The fifth term, 5 squared is 25, and so on. This was our general formula for that sequence. This series would have the same general formula that generates the terms of that sequence. 1 plus 4 plus, that generates the terms of this series. 1 plus 4 plus 9 plus 16 plus 25. But once we know the formula that generates the terms of the series, we usually write it in what's called sigma notation. Okay? Use the a sub n formula for the series to write the series in sigma notation. Just like that. Sigma is a Greek letter. It's from the Greek alphabet, and that is this letter right here. Okay, which you may have seen in other math situations. That is the capital letter sigma from the Greek alphabet, and that is the universal mathematical symbol for adding stuff together. And in the context of series, it means this. Take the terms of a sequence and add them together to get a series. So since we know that this series is generated by the terms, each member of the series is generated by this formula n squared, I'm just going to write it like that, n squared. And I'm going to designate like this. And that is this series here written in sigma notation, where that says add together from n equals 1 up to 5, meaning the first 5 terms of the series whose each individual terms are generated by n squared. So working backwards, the first term would be 1, because 1 squared is 1. The second term would be 4, because 2 squared is 4. The third term would be 9, because 3 squared is 9. Fourth term would be 16. Fifth term would be 25. So what we've done is we've taken this series, which is written in sigma notation, and we've expanded it back out into its expanded series notation. If we wanted to, we could evaluate this series and write down the sum of this series and get 55. Sigma notation, expanded form, sum of the series. Okay? Very good. Okay, so let's do some other examples. Okay, and I've created a classwork example for you guys to work on. So let's do a couple of examples here of each kind of thing that you're going to need to be able to do. And really all we want to know right now, the biggest thing right now is, or one of the biggest things is be able to understand, okay, yeah, that's sigma notation and what that means, okay? So I'm going to put this aside here, put this over here, and we're going to do some examples here, like this. So examples. So number one, okay, so let's say we've got, I write this out here, and this is going to be a series in sigma notation. And by the way, the math problems won't always use n to designate the position. It's just a counter, tells what position the term is in the series, so it could be any number. So in this case, we're using a, a sub 1, a 2, a 3, a 4 to give this terms in the series. And let's say what we want to do here is we're supposed to rewrite this in expanded form. Well, that means we're actually using the formula here. We're actually going to calculate what the first three terms of the series are, right? So first, thinking about them in terms of a sequence first, the first term would be 3 times 1 plus 1. The second term would be 3 times 2 plus 1. The third term would be 3 times 3 plus 1. This says the first, expand out and write it out as a sum of the first three terms. The first one, the second one, and the third one. This is 4, that's 7, this is 10, and so in expanded form, that's what we write. That's the series written out in expanded form. Or let's say we had this one here, and I'll say n for this one. N is equal to 1 to, or let's say m is equal to 1 to 5 of negative 3n plus 8. This says write out expand out the first 5 terms of the series, whose formula that generates the terms of this series are negative 3m, that should be an m there, negative 3m plus 8. Well, we just in turn put 1 and then 2 and then 3 and then 4 and then 5 in to generate the first 5 terms. So the first term is negative 3 times 1 plus 8. The second one is negative 3 times 2 plus 8. The third term is negative 3 times 3 plus 8, and so on, right? So this is 5, this is 2, this is negative 1, and then the next terms, if we do the fourth term and the fifth term, I didn't write them out here, the fourth term and the fifth term would be negative 4 and then negative 7. Okay? And oops, it's not a sequence, it's a series. So here, we've generated the first 5 terms, 5, 2, negative 1, negative 4, negative 7, and then we've written them as a sum because it's a series. And that's the expanded form of that. Okay, does that make sense? That's how you rewrite numbers in if you start with a series in sigma notation, you're rewriting in an expanded form. Okay? Okay, now, on the other hand, okay, so that's how that goes. On the other hand, you might, so this is rewrite in expanded form, okay? Let's say you had to evaluate, okay? That means you take each, once you've written it out as a series, you actually add them together, right? So example 3, if we had to evaluate this series, well, we'd write out 4 plus 7 plus 10, right? And then we'd add those together. That works out to be 21, I think. So yeah, that is the sum of this series here, this finite series here, and that's how we evaluate it. Or number 4, okay, this one here, if we had to evaluate this series, like that, well, first we'd write out the first 5 terms like we did here. 5 plus 2 plus -1 plus -4 plus -7, right? And then we'd actually add those together. And unless my arithmetic is completely falling apart, okay, that works out to be well, let's actually work it out. That's 7. Minus 1 is 6, right? Minus 4 is -10, and then minus 7, I think that's -17, right? 5 plus 2 plus, I never trust my head arithmetic, 5 plus -4 plus -7. That's not what I did. 6, yep. Okay, bad arithmetic. -5. I got to here and said -7. Anyway, so that works out to be -5. So this is the sum of those first 5 terms. That's the sum of this series, and it's been evaluated. Okay? Very good. Okay, so that's how that goes. Okay, so this is evaluate. Okay, now I'm going to give you one to try out. Okay, where you're going to expand it, and then you're going to write it in, and then you're going to evaluate it. And this is in sigma notation. This is example 5. You try. Okay. I'm going to say for this one, n is equal to 1 to 4 of, let's say, 2n squared. So first off, expand this out, what the first 4 terms of this sequence would be in a sum, and then evaluate, actually find the sum of that series. Okay, so I'm going to stop now. You should put the video on pause and try this out on your own. Okay, good. Okay, so the first 4 terms, okay, this would be 1, okay, we put 1, then 2, then 3, then 4 in turn. So 1 squared times, so that's 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared plus 2 times 4 squared, like that. So this is, as you can see here, 2 plus 8 plus 18 plus 32, right? And then that's 48. I think that is equal to 60, right? So that, oops, I should put that down there. Sorry, getting ahead of myself. That's this expanded series. And then when we actually add those together, we get 60. That's what you get when you evaluate. Okay, very good. Now, another example, which you're going to have to do sometimes, and this is maybe the hardest part here, is you're going to be given the terms of the series, and you've got to rewrite it in sequence form. Or rewrite it in, okay, so rewrite series in sigma notation, right? So let's say you have this one, 2, 4, 6, 8, 10. So we're going to do the opposite of what we just did up here. We've been given the expanded form, and we've got to work backwards to this. So what you've got to do, you've got to think about, okay, well, what's the formula? First off, we can see that we're going to put the sigma down, and we're adding up 1, 2, 3, 4, 5 terms. So we're going to write n is equal to 1 up to 5, because it's the first 5 terms of the series. Now we need to have a formula that generates those terms, starting with 2 being the first term. Well, we think that's the first term, that's the second, that's the third, that's the fourth, that's the fifth. And we can see that each time we're multiplying our n number by 2. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So in general, a sub n in this series would be 2 times n, right? And that's what we write over here. Okay? Or, so that was example 6. So here's example 7. It'll be the last one before I let you go on this one. Let's say we had this series here, 3, 9, 27, 81. Okay, well, so again, oops, and that's not supposed to be commas. It's not a sequence, it's a series. The terms are adding together, right? So we see, first off, we want to put the sigma down to show that we're adding those together. And we see that there's 4 of them. So n is going to be equal to 1 up to 4. And now we have to think, well, what's the formula that generates those? Well, we think, oh, look, that's the first term. That's the second term. That's the third term. That's the fourth term. Well, can you see that we're actually raising these to a power of 3? That's 3 to the 1. That's 3 to the 2. That's 3 to the 3. That's 3 to the 4. So 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. So can you see, in general, a sub n is equal to 3 to the n power. So that is the formula that we're going to write over there. Okay, so that is a series written in sigma notation. Okay, very good. Okay, so that's it for this one. There's going to be another addition, another 1 or 2 additions for today's lesson about arithmetic series, a specific kind of sequence in series called arithmetic sequences in series. Stay tuned.